Hi, this is Alan Haungs, a lecturer, Professor Alan Haungs, SUNY at Fredonia, for the Oscilloscope Lab, basic concept number 2 for the Physics 124 class. Just as a review, we're going to be using the oscilloscope to measure voltage signals, and voltage signals exist with very little energy. There is energy involved, so we're not going to be talking about power when we're talking about electricity. In this case, we're just speaking of voltage. There is a slight current that exists to create a signal, but it's not worth discussing. So signals are used for communication. For example, speaking over a phone, the audio signal that transfers information. It's used for control. Uh, when my Mini Cooper lost its cooling system, a signal came from a sensor. The signal tells the computer don't allow the engine to operate at full power. So I was able to get home without a cooling system because it was controlled. The power was controlled and preserved the engine. So a signal and a sensor. So it's used for control, communication, and computing. Inside of a computer chip are hundreds or millions of little circuits, and little voltage signals are going in and out of these circuits. So all these things electrically exist in your very own body. Your eye communicates with your brain via electrical voltage communication. Your heart is controlled by your brain partially. If you want to speed up your heart, just be startled and your brain will give it a signal. So you have control, and you also have computing in your brain. So using electrical voltage signals for in nature is a very common thing. In addition to now as an engineering thing, it's also what we do. Getting back to the oscilloscope, oscilloscope is a very general concept. So there are certain things that they have. All of them have. If we're talking about a laboratory oscilloscope, they all share these in common. They all have a selectable vertical gain so that you can measure a large variety of voltages. They have a selectable horizontal sweep time, so it goes boom, boom. So that slow part, that's the sweep time, and you have several selections so that you can measure a large variety of sweeps, and then many of them, or I would say any of them in a laboratory setting, come with a dual input, meaning that you can actually measure two voltage signals simultaneously and see them both on the screen simultaneously, and I'll explain why that's important. And then they all have something called a trigger level. The trigger level is essentially a way for the scope to create a very stable picture so that you can see it. It looks like it locks it right into space. So let's get right to it. Why would we want dual control? Dual input. Well, let's say if you had a circuit that had an input that looks like this, but its output looks like this. You can see this is 90 degrees phase shifted. That might be something that's very undesirable in some circumstances, and then in other circumstances it could be not even important. In others, it could be very desirable. In engineering, we actually make circuits that's called a differentiator or an integrator that would actually result in this kind of behavior. That was the input, that would be an integrator. That's the negative sign. This is a sign. A negative cosine, that's a sign. So that's a definite integral of this. So, for example, if you were, let's say if you had a speedometer that puts out an electrical signal, so there's a correlation between the voltage out and the speed. If you fed that through a differentiator, that would tell you the instantaneous acceleration at that moment. That circuit, that would have an output voltage that would represent that instantaneous acceleration. If you put it through an integrator, it would give you the overall number of feet or meters that you traveled. And so that would keep a running total. So signals, that do this are sometimes desirable, sometimes not. Sometimes with sound systems, if this occurs, it creates a problem. Other times it don't. The other issue too with the dual input, like say if you had an input that looks like this, nice and clean, and then you get this little chop at the top here at the bottom, that's called harmonic distortion. If that was a sound system, it would sound terrible. So you could use this to troubleshoot. You say, well, my input looks perfectly fine, my output looks terrible. Or if your output looks like this, you'd say, look at all the noise. There's some kind of electrical interference, radio signal, something, the power supply, or something is causing that loose connection. So it could be used for troubleshooting. Another thing too is like with this example here. Let's say if this was a speaker, and then we move, and this is an input, so this is what we're putting into a speaker, the electrical signal. And then say this is the electrical signal coming out of a microphone that's being removed from the speaker. So if we see that there's a delay here, and we see the peak here was that peak there, and we know the time from here to here, we know the time that it took this wave to reach that speaker. Just by doing the measurement of the distance between the speaker and the microphone and knowing this time, we could actually figure out the speed of sound through air. So you could use this cleverly for analyzing something in the physical world. Let's talk about vertical gain. Now, like I said, the oscilloscope is like a TV. And so it has permanently drawn little marks like this on it. Those are divisions. That's a division. And then you'll see little subdivisions. So that's not what I'm talking about when I say division. So they're divided into 5. 1, 2, 3, 4, 5 on my oscilloscope. So you got little subdivisions, but you got the major divisions. So when I'm talking about divisions, I'm talking about the major. These little divots in there, so you can do estimates should something fall in between. So the vertical gain on my scope is between 5 millivolts to 5 volts per division. This is the vertical gain. That means if I have something that goes like this, if I had my vertical gain set to 1 volt per division, and if I said to you, what is this voltage right here? And if it's 1 volt per division, it'd be -1, -2. So that voltage there would be -2. If I said it was 10 volts per division, if I set the knob, click, 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 10, that would be -10, -20. If it was 1 millivolt, this would be -1, -2. So you could do this. So this is, and you would go like this. You'd estimate this one, and that's how that would work. If it falls in between, the amplitude falls somewhere like this one falls here. You got those little subdivisions. You figure out the best you can to make an estimation. So that's how the vertical gain works. You set the knob to get the best picture so you can read things as easy as you can. Now let's talk about time base. Time base has to do with this. Remember I mentioned scan and then instantly come back. Scan, then instantly come back. So time base has to do with this scan. And it has to do with how many seconds are in one of these divisions. So it's time per division. It's usually seconds per division, right? It's seconds per division. So essentially, if I have a wave that looks like we'll go like this and like this and like this. Okay, hopefully I drew it right. Okay, so how many time divisions did I go through for one complete cycle, one complete period of a sine wave? I went through 1, 2, 3, 4. Okay, I went through 4 of them. If I said that these were 1 microsecond, each division, if I set the dial for 1 microsecond per division, it'd be 4 times 1 microsecond. That would be the complete period time of that wavelength, of that wave. Not wavelength, but wave. Um, wavelength, you usually refer to that when you're speaking spatial, not temporal. So again, so my machine goes from 0.2 microseconds per division to 2 seconds. So it'll literally crawl across the screen like this, 2 seconds, and I can hit another multiplier, make it 20 seconds. It's, tortuously slow. So let's see. So if this was once, so if I'd set it for 1, if I'd set this for 1, right, it would be 1, 2, 3, 4. So it took 4 seconds for a period, right? And remember that frequency equals 1 over the period. Period is the time it takes for one complete cycle to occur. That's a period right there. That's a period. That distance right there. See it? That's in time. Okay. The other feature that almost any oscilloscope would have, or I should say all of them have, is something called a trigger level. A trigger level. So just imagine if you have this thing right here, and you set your sweep, and so you get this nice smooth line. But let's say your sweep doesn't perfectly synchronize each time at the same point on this line. So what would this little mountain do? Well, the mountain would start to either roll forward or roll backward. It would be rolling on the screen. If it was rolling really fast, you'd see nothing but a blur. So how can we lock this in to the screen while we simultaneously keep the base time for the sweep the same, the seconds per division? How can we do these two seemingly they compete against each other ideas? How do we do that? Well, we use something called a trigger level. So if I set it for, if I set this for 1 microsecond per division, well, it would still do the same thing. Every microsecond, that little dot would move a division, a division, a division. But if I set the threshold, the trigger threshold for -2 volts, increasing, and the way you do this is what you do is you play with this knob, and suddenly the picture freezes and where you like it, and you leave it. You don't know it's -2 volts, but let's say if the vertical gain here is 1 volt per division. So right here is -2. If while I'm turning that knob, just watching the screen, this is not a calculated thing. This is purely subjective. When I see that screen freeze like this, I have inadvertently set the trigger level for -2 volts while the voltage is increasing. It's on an upward slope. What will happen is that trigger will say, do not begin the sweep across until you see -2 volts and the signal is increasing. Now do the sweep. And then it'll wait. And then it'll wait until it sees it happen again. -2 volts increasing. Okay, go back. Then it'll wait. Maybe a few of these cycles will pass. They won't show up on the screen. Then it'll find -2 volts increase. Goes back. So it produces this beautiful stable curve. And if it's occurring quickly, you wouldn't know that you're missing. You would not even know that things aren't being retraced over the top. It looks perfect. So we're going to do the demonstrations next and have some questions. And you guys have a great day.